Scale is a book with a transdisciplinary spirit. It presents the fundamental scaling principles which is found universally. The author, Geoffrey, is a theoretical high-energy physicist. He expanded his knowledge in the field to expound the universal scaling law in seemingly unrelated subjects such as biology and the structure and dynamics of socio-economic sciences via the language of statistical mathematics. Throughout the book, you will see that the remarkable scaling laws regulate almost all measurable characteristics of animals, plants, ecosystems, cities, and companies. The author expounds the nature and origin of these systematic scaling laws by addressing questions such as, why can we live for up to 120 years but not for 1,000 or a million? Why do we get far fewer tumors than mice, but whales get almost none? Why do we stop growing? Why do cities keep growing and last long? Why do almost all companies live for only a relatively few years? The very first scientific argument about scaling was articulated by Galileo Galilei. In his book Discourses and Mathematical Demonstrations Relating to Two New Sciences, published in 1638, he asked what happens if you try to indefinitely scale up an animal, a tree, or a building. And he made the following pronouncement: "You can plainly see the impossibility of increasing the size of structures of ships or palaces of enormous size, nor can nature produce trees of extraordinary size, because the branches would break down under their own weight." Why is that? Let's consider a simple geometry. The area and volume scale up at different rates. When the length is doubled, the area increases with the square of the lengths, but the volume increases with the cube of its linear dimensions. Thus, when an object is scaled up in size, its volumes increase at a much faster rate than its areas. Galileo showed that the strength of pillars holding up buildings, limbs supporting animals, or trunks supporting trees is proportional to their cross-sectional areas. The weight increases in direct proportion to its volume, scaling as the cube of the length, and this is much faster than the corresponding increase in strength provided by its cross-section. Let's imagine that a small teddy bear got transmuted and increased by a factor of 100. Then the weight needed to be supported increases a millionfold, whereas the strength of its limbs holding it up increases by only 10,000-fold. Thus, the ability safely supports the additional weight of only 1% of what it had previously been. Eventually, this gigantic teddy bear will collapse under its own weight. In other words, relative strength becomes progressively weaker as size increases. But people have the natural propensity to think linearly and erroneously that doubling the size leads to a doubling of the strength. The scaling misconception caused many problems in different areas throughout the history. Isambard Kingdom Bruno, an English civil engineer known as one of the most ingenious persons in engineering history, designed the Great Eastern, the largest steamship ever built at the time of her launch in 1858. Economically and technically, however, it was not a success. The lack of a deep understanding of the basic principles of scale, the ship could barely move her gargantuan mass at even moderate speeds. In the medical and pharmaceutical science, determining how to scale up a safe and effective dosage of drugs according to the body weight has been and still is a critical issue that is yet to be solved. In one of the researches conducted in 1962 to investigate the effect of a dosage, a very atypical model animal, an elephant named Tusco, was chosen. He weighed about 3,000 kilograms, and the researchers estimated that a safe dose for him should be about 0.1 milligrams per kilogram multiplied by 3,000 kilograms, which comes out to 300 milligrams. The results were catastrophic, and it didn't even take 5 minutes for him to collapse after the injection. This naive and erroneous assumption that safe dosages scale linearly with body weight led to the disastrous consequences. So the search for the fundamental scaling laws began. This is related to the new science of complexity of the 21st century, with the observation that there is a fundamental principle that governs how the complexity emerges from its underlying simplicity. Most complex systems such as life, society, and companies can be viewed in terms of their information and energy transfer. In life, this means that the genetic code stores and processes the information of the organism, and the metabolic system transforms energy for maintenance, growth, and reproduction. All the biological activities are supplied by metabolic energy. Therefore, metabolic rate is the fundamental rate of biology, setting the pace of life. Despite the extraordinary diversity and complexity of life though, metabolic rate plotted logarithmically against mass exhibits an unexpected systematic regularity across all organisms as a straight line. You can see that for every 4 orders of magnitude increase in mass, metabolic rate increases by only 3 orders of magnitude. Consider a cat and a mouse. The cat is 100 times heavier than the mouse, but the metabolic rate of the cat is only 32 times greater than that of the mouse. If we consider a cow that's 100 times heavier than the cat, its metabolic rate is likewise 32 times greater than the cat's. And if we extend this to a whale that is 100 times heavier than the cow, its metabolic rate would be 32 times greater than the cow's, an explicit example of economy of scale. This graph is the number of heartbeats per lifetime plotted against the weight of a series of mammals. As you see, the number of heartbeats in a lifetime is approximately the same for all mammals, 1.5 billion times. For example, the shrew has a heart rate of roughly 1,500 beats per minute and live for about 2 years, whereas the heart rate of whales are only about 30 beats a minute, but they live for about 70 years. The mechanistic origins of the scaling laws in biology are rooted in the universal mathematical, dynamical, and organizational properties of the multiple networks that distribute energy, materials, and information to local microscopic sites that permeate organisms. These independent generic network properties can be summarized into 3 categories: space filling, the invariance of terminal units, and optimization. Space filling simply means that capillaries have to service every cell in the organism. The invariance of terminal units means that the terminal units, such as the capillaries, all have approximately the same size and characteristics regardless of the size of the organisms. For example, the diameter of capillaries of all mammals, whether mice, deer, or elephants, are essentially all the same. All these ongoing processes have been optimized over enormous periods of time through continuous multiple feedback and fine-tuning mechanisms of natural selection to minimize energy usage and maximize efficiency. With the network theory for understanding scaling laws, the question can be now extended to whether its framework could be used for other network systems such as cities and companies. Cities are complex, adaptive social network systems resulting from the continuous interactions among their inhabitants. This is a logarithmic plot of infrastructure quantities associated with transport and supply networks against the size of cities. They include the total length of electrical lines, road, water, and gas lines. What is quite surprising is that these various quantities all scale in much the same way across the globe. The scaling is sublinear because the slope of the straight line is less than 1. It indicates a systematic economy of scale, meaning that the bigger the city, the fewer the number of infrastructure is needed on a per capita basis. So as far as their overall infrastructure is concerned, cities behave just like organisms. In contrast to infrastructure, socio-economic quantities such as average wages, the number of professional people, the number of patents, the amount of crime, and the gross urban domestic product scale with approximately the same slope greater than 1 regardless of the urban system. So socio-economic quantities scale superlinearly, thereby manifesting systematic increasing returns to scale. These results are quite amazing because it means that our own urban systems are approximately scaled versions of each other, regardless of unique history, geography, culture, and character of each city. So how is this possible? Recall that the generic geometric and dynamical properties of biological network that underlie the scaling law are the space filling, the invariance of terminal units, and optimization. These properties have direct analogs in the infrastructural network of cities. For example, our transport networks and utility lines have to be space-filling so that the terminal units, in this case, every local region, house, and building of the city, are serviced in the most cost-effective, optimized way, which results in a sublinear scale. Companies are fundamental elements of the socio-economic life of cities and states. A crucial aspect of the scaling of companies is that many of their key metrics, such as profits, assets, or sales, scale sublinearly against their size like organisms rather than superlinearly like cities. Their sublinear scaling therefore suggests that companies also eventually stop growing and ultimately die out. This plot shows the mortality probability for companies due to bankruptcy or liquidation versus their age. Regardless of the size of their sales or business categories, their mortality curves show that the number that have died reaches almost 100% within 50 years. In order to achieve greater efficiency in the pursuit of greater market share and increased profits, companies add more rules, regulations, and protocols at increasingly finer levels of organization, resulting in the increased bureaucracy. This is often accomplished at the expense of innovation and R&D, which should be major components for its long-term future. This is a classic recipe for eventual disaster. Indeed, the scaling laws for the highly complex systems such as organisms, cities, and companies reflect systematic regularities, suggesting that possible quantitative and predictive science of such systems might be attainable. As the author concluded, this book demonstrated that grand syntheses that transcend the narrow confines of disciplines are not only possible, but also agree with the fundamental tenet of science that the world around us is ultimately governed by universal principles.